Welcome back to Engineering Acoustics. Hi, this is Professor Ryan Harne. We do not perceive sound levels as being equal across frequency and amplitude. In this video, we'll learn how sound levels are weighted to account for this sensitivity.
So let's get started. Not only is human hearing sensitivity to different frequencies nonlinear, but human hearing sensitivity to different sound levels is also not linear. Take for an example something taken from our equal loudness contour plot. A sound that's actually played at 40 decibels at 1 kilohertz will be perceived as being at 40 decibels. But the same sound, if played at 100 hertz, would have to be turned up to be 62 decibels to be perceived as being 40 decibels. This motivates a weighting scheme in our reporting of sound levels that is psychologically or physiologically relevant. Weighting networks are then defined that add or subtract values to SPL reports so that we better approximate the physiological response to sound. A weighting accounts for human hearing to low and moderate sound levels. A weighting is the most widely used weighting network. C weighting accounts for human hearing subjected to impulsive and loud sound levels. C weighting is sometimes used in defense and security applications of sound reporting. So we report dBA as being equal to the decibel value of sound pressure level plus an A weighting. Likewise, dBC is the dB recording plus a C weight. Let's look closer. Let's apply an example of A weighting for octave bands. We see the octave band center frequencies shown in the first row, and the second row shows the A weighting that would be applied to a decibel value. So if we consider our octave band results at the right, we add the A weight to our dB value. Grabbing the data from this plot, we see that at 32 Hertz, we have a 38 decibel reading of sound pressure level. At 63 Hertz frequency band, we also have 38 decibels. At 125 Hertz, we have 47. At 250, we have 50. At 500, we have 75. At 1000, we have 76. At 2000, we have 70. 4000, we have 60. 8000, 55. And at 16 kilohertz, it's not presented on this plot, so that's not applicable. Let's find the dBA values weighted from these decibel readings. So that means we add the A weight to the decimal value. For the 32 Hertz octave band center frequency, if we add the minus 39.4 dBA to our decibel reading of 38, it would be a negative value. So instead, we simply report the dBA in this case as being 0 dBA. For 38 decibels at 63 Hertz, we would get 11.8, which is really just 12, since of course we don't use decimal decibels. At 125 Hertz, the difference and then rounded would be 31 dBA. At 250 Hertz, the 50 decibel reading would be 41 dBA after conversion. And likewise, going down the row at 500 Hertz, we have 72 decibels. At 1000 Hertz, there is no positive or negative A weighting to apply because humans hear 1000 Hertz as approximately being equal to the subjective value. So we have 76 dBA just as we would have 76 dB at 1000 Hertz. At 2000 Hz, we have approximately 71 dBA. This is greater than a dB value because humans are more sensitive at this frequency range from around 2000 to 4000 Hz, such that the A weightings are actually positive values. So at 4000 Hz, we add 1 dBA to the dB to find 61 dBA. Continuing to 8000 Hz, we subtract 1.1, which when rounded is simply 54 dBA. So we find that the dBA value is the sum of the A weighting and the dB recording. These tables show all of the A and C weighting values for the frequencies shown in the left columns. It is important to note that A and C weighting is not applied to narrowband readings. The frequencies that are shown in the left columns correspond to center frequencies, lower frequencies, and upper frequencies only of 1/3 and octave band frequency bands. Finally, the OASPL, the overall sound pressure level, is often reported in dBA and not dB. But it's important to understand how it's computed. To compute the OASPL, we first compute octave band values of sound pressure level in decibels. We then apply A weighting to our dB readings to get our dBA values of the octave band SPL. Then we compute the OASPL and dBA from the equation 10 log 10 of the sum of 10 to the power SPL divided by 10. If we perform this routine for the plot at the right, our dBA values are shown in the bottom row of the table. OASPL in decibels for this plot would be 79 decibels. But OASPL, once weighted for dBA, would be 78 dBA. It is not always the case that OASPL will go down when converted to dBA. It is a matter, though, of where the frequency content is concentrated in the given recording. So let's summarize what we've learned. We often report sound level pressure that's weighted, especially in the dBA scale, and this accounts for the human hearing sensitivities in frequency and in level. Weighted SPL values are calculated by the sum of the octave band SPLs and the dB correction. Finally, OASPL, the overall sound pressure level, is most often reported in dBA, and it's of significant utility in many noise control practices.
That's it for this video. In the next video, we'll learn how weighting networks and frequency bands are used in the standard tool to measure overall sound levels.